Hi, everyone, and thank you for showing up for your learning. Oh, you're all more than 6 feet away. I'll do this while I do the lesson. That way you can see that I am indeed smiling under the mask as I peer at you in the back of the class. Today's goal is we want to make sure that by the end of the lesson that you can simplify algebraic expressions containing integer exponents, and you can add this learning goal as well, evaluate exponential expressions. So if it's only numbers in there and it's not a function, you want to be able to find out what the number equals. So those are our two learning goals for today. So let's carry on and we'll see what we need to do. First, let's take a look at some definitions. These are the words that I'll be using to discuss exponentials throughout the unit. We want to know what a power is. And in this case, this whole part here, x to the 7, and you can improve the writing there if you want, x to the 7. This is all a power. And a power is composed of two things, a base and an exponent. So the base is here. This is the base number. And then this number here is the exponent. I zoomed in far too far. I should improve that for you next time. So if we were looking before at x squared, these were quadratics. X was always our base for the exponent. And squared, the 2, was the exponent. But this unit is going to flip the script. Now, in this unit, we're going to have a base that's a number, and the exponent is going to be the variable now. So this is now what we're going to be looking at. This is still the base, but now the variable is the exponent. And we can also have coefficients as well with these things. Like here, 3 multiplied by x to the 7. 3 is the coefficient, and it's not part of the power. So a power is a base to an exponent. The exponent is the number up top. The base is the thing that's being raised to the exponent, and blah, 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 blah. So let's take a look at a situation where we're going to use exponentiation to understand it. Let's say a video is going viral. Viral videos tend to grow exponentially. The more people that see it, the more people that share it. And as more people share it, more people see it. So then the next generation of sharing is bigger than the last one, and it grows exponentially. And this is why these things can blow up in our society. So let's take a look. If we have a viral video and it's doubling its views every hour, and it only has one view in the hour after it's published, let's try and find out how long it takes to get 1 million people seeing that video. Let's guess. How many hours do you think it's going to take for 1 million people to see that video? If it only has one view after 1 hour, but every hour it doubles. Do you think it's going to take several days, several weeks, months, or is it going to happen within a day? 5 hours? One guess? More guesses? 100 hours? We want this to go over 1 million. 15 hours? Okay, let's take a look. Here's one way we could solve this question. We could have x be the number of hours, and we could make a table. And then this would be views. Views is spelled with a V, V-I-E-W-S. Okay, there we go, views. Let me erase my mistake there. Views. In x is 1, we know that there's one view. After 2 hours, how many views will there be? 2. And after 3 hours, how many views will there be? 4. It's doubling. And after 4 hours, how many views? 8. 5 hours, 16. And we keep going. And another way that we could do this, we could expedite this process just by doing it on our calculator like this. You take 1 and go multiply by 2, and then push equals, and that's 2 hours, and then just count them. 2, 3, 4, 5, 6, 7, 8, 9, 10 hours. After 10 hours, 500 people have already seen it. 11, 12, 13, 14. After 15 hours, 16,000 people have seen it. 16, 17, 18. After 18 hours, 130 people have seen it. So we could put that into our chart. 18, 130K or so. Let's keep going. It's 131,072. 19, 20, 21 hours. From one view, and then everyone who's seen it shares it with one person every hour so that it doubles its views every hour. 1 million views after 21 hours. So that was pretty fast, right? If we write this out, this is what it looks like. We would say 2 times 2 times 2 dot 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 times 2 21 times. Multiplying 2 by itself 21 times. Obviously, writing that out as 2 times 2 times 2 times 2 times 2 times 2 times 2 is not something we want to do. Okay? It's much too much writing. So that's why we have a new notation system for this type of situation. We would write this as 2 to the power 21. So 2 multiplied by itself 21 times will give us that number. And that's what we mean by this exponent. It's telling us how many times to multiply the base by itself. Okay? So we can have a therefore statement. Therefore, after 21 hours, 1 million people or more people will have seen the video. Okay. And so now go ahead to the next page. And one thing that's going to be really useful to have for this unit and to be able to answer questions quickly and to have as a reference is a table that you can use for different powers. Just like we have a multiplication table up here, you could create a powers table. And having powers of 2, 3, and 5 is going to be enough to get through the unit, knowing your powers 2, 3, and 5. Powers of 7, use your calculator. Powers of 6, you could use the power of 2 multiplied by a power of 3. Powers of 4 are just powers of 2 in another form, and we'll see how that is later. But powers of your primes are useful to know. So let's go ahead and fill in this chart. First of all, what you could do is write these out as 2 to the 1, 3 to the 1, and 5 to the 1. What's the meaning of something to the 1 power? What does that mean when I raise something to the power 1? Just about, Kate. You're not wrong. It kind of just means just multiply by that number, but only one time, please. Multiply by 2 once is 2. I'm 42 to the 1 years old. No one's ever been 42 to the 2 because that's a really big number. 42 times 42, no one's that old. But raising a number to the power 1 is just that number, so you could put that in there as 3, 3, and 5. Okay? And then, how about 2 raised to the power 2? What is that? Well, it's just 4. It's 2 times 2. 3 to the 2? 9. And 5 to the 2, what's 5 squared? Yo, what's 5 squared? 25. So these are the parts of the table that you can probably do in your head. See how much of the table you can complete in your head, and then circle the part where you start using a calculator. Just as a way of reflecting on your own knowledge and seeing if you can grow that knowledge over the course of the unit. Can you expand your list of powers 2? Can you expand your list of powers 5? Work in the positive direction to start, where here I'm going to raise 2 to the power 3, so 2 to the 3 would be equal to 4 times 2 is 8. Okay, I'll pause the video. You can go ahead and fill in your chart, and then we'll take up our charts together in just a moment. So one great question is, how do we type these into our calculator? And one way to do it is the hard way, which is I'm going to go 5 times 5, and then say equals, that's 5 squared, 5 cubed, 5 to the 4, 5 to the 5, 5 to the 6, 5 to the 7, 5 to the 8, 5 to the 9. So notice that that number there is the number that I have here, and it's there. but you certainly don't want to have to punch it that way every time. Let's say we want to know how much money will you have after 60 years, and you have to multiply 1.1 by itself 60 times. You don't want to enter 60 times. It's so easy to make an error. So this is the button that you're going to want to find on your calculator. It's going to look like this. If I do this button, like 5, and then the X to the Y button is usually how it's written on a calculator. So I do 5 to the 9 equals, and there, it just outputs it. And the little calculator brain multiplies 5 by itself 9 times to tell me that number. So that's how it's punched. Yeah. Now, this is our table so far. I have circled where I run out of my memorization, so I have that one memorized, but I could do it like in my head to there, and then I got bored and used a calculator on the way down, used a calculator down there. I'd like to memorize some more values. Maybe you have a few fewer values memorized, and that's okay. We'll work on it over the course of the unit. But notice I included powers to the 0. So 2 to the 0, 3 to the 0, and 5 to the 0. Anyone know how to calculate those without a calculator? Or know the rule there for to the 0? Dominique? They're not 0. Try it on your calculator. What do you get? Well, let's go. I'm going to put a 2 in as my base, and I'm going to raise that to the exponent 0, and I get 1. Let's try a different number. 5 raised to the power 0 is 1. I wonder what, let's try 1,400.3 raised to the power 0. What's your prediction? 1. Oh, wow. It seems like whatever I put in there to the 0 gives me 1. Isn't that interesting? Anything to the power 0 is seeming to give me 1. Okay, so these are all equal to 1. And all of them have the same value. It doesn't matter if I have 3 to the x, 5 to the x, or 2 to the x. If I gave you an expression like 2 to the x equals 3 to the x, then x could be 0, and both sides of the equation would be equal to 1. So that would be a solution to that equation. Now, what if I have negative exponents? Let's investigate with my powers of 2. Okay, so this is how you can investigate on your calculator. Put in 2 as your base, and raise that to the 1, but it's negative. Any predictions on what I'm going to get? I had some groups saying that that's going to be equal to negative 2. And I told them it's not. Yeah, oh, very good. Yes, this will be equal to 1/2, 0.5. Okay, let's see if we can notice a pattern here. Rather than writing that down as 0.5, I'm going to astutely write that down as 1/2. Okay, that's 2 to the negative 1. Let's experiment. What's your prediction of 2 if I raise that to the power 2, negative 2? 2 to the negative 2, what's your prediction? If 2 to the negative 1 was 1/2, what will 2 to the negative 2 be? Any guesses? Let's try. It equals 0.25. What's that as a fraction? If I write, how many cents is that? 25 cents, right? If I say 25 cents by another name? That's a quarter. Ah. So 2 to the negative 2 is 1/4. What's 2 to the negative 3 going to be? 1/8. Good. 1/8. Okay, so notice these did not become negative values. When I have a negative exponent, that's like saying here 2 to the negative 1 is equal to 1/2. 2 to the negative 2 is equal to 1/4. Well, that's just 1/2 squared. And 1/8, that's 1/2 to the 3. It just flips. This value here puts it on the bottom of the fraction. This value here puts it on the bottom of the fraction. This value here puts it on the bottom of the fraction. So we see the negative exponents just flipping our base. Okay? What's 3 to the negative 1? Sorry? Okay, what's that as a fraction? Oh. So if I have 3 and I raise that to the power negative 1, it gives me this weird decimal, 0.3 with a lot of 3's after it. What is that as a fraction? 0.3 repeating. What's that as a fraction? It's 1/3. Good. Yeah, it's 1/3. It just 3 to the negative 1 is just 1 over 3. And then 3 to the negative 2, well, that's going to be 1 over 9. And 3 to the negative 3 is going to be 1 over 27. Okay. Notice that it just takes this number here and puts it on the bottom of the fraction. This number here puts it on the bottom of the fraction. You could use that idea to extend your table to the negative 9 if you wanted to, but you don't really need to do that. Just need to be aware of what's happening here. What's 5 to the negative 1? Let's test our calculator. Yes, 1 over 5. So if I 5 to the 1, but it's negative, I'll get 0.2. 0.2 is 1/5. That's, 5 of those makes 1, so 1/5. There you go. So same pattern here. This is 1 over 5, 1 over 25, and 1 over 125. There you go. All right. So the big trick here is if you can walk away from today's lesson understanding what negative exponents are up to, and you don't make the same mistake throughout the unit, which is a negative exponent and you believe for some reason it makes the answer negative. It's not. It's making the answer very, very small. It's making the answer go to the bottom of the fraction. How are you going to write an example to help you remember here? It might look something like this. 5 to the negative 3 equals 1 over 5 to the 3 equals 1 over 125. Hi, Sydney. I want to grab a hand. Oh, there is a handout there for you. Yeah. So you might use an example like that to help you remember. Or maybe you have something like x to the negative 2 is going to be equal to, I don't know what x is, but this is going to be equal to 1 over x squared. How would you describe this negative exponent? Like, what's it doing? We have this language here that this is the base of the exponent here. This is the exponent. If the exponent is negative, what is it doing to the base? How would you express that? This is what I would say. Fine. Yeah. A negative exponent will flip the base and put it under 1. So that's one way that you could remember it. Put it under 1. Yeah. If you have x to the negative 2, that's 1 over x squared. The reason is, well, yeah, we're going to look at this a little more, just the next page. Okay. Keep going then, shall we? Well, don't mind if I do. Let's get some exponent laws on the next page. All right. So our next page, we're going to take a look at the various exponent laws, and I expect all of you encountered these in grade 9. I also expect that higher than 90% of you have forgotten some or all of these since grade 9. I forget them all the time. And when you forget them, I'm going to show you the tricks that you can use to reteach yourself. Forgetting is a natural part of learning, and it's the recalling of information that's difficult that makes learning happen. It's like when you struggle with something, that struggle tells your mind it's important, and then it stays in your mind a little better than had you not struggled. So I'll show you how to struggle with this and use multiplication something that we all understand a little bit better than exponentiation, to reteach yourself the exponent laws. Okay. Our first rule is product of powers. Okay. The product of powers rule says when you're multiplying powers of the same base, you are going to add the exponents. And let's take a look at something like if I had x to the a multiplied by x to the b, that's going to be equal x to the a plus b as the exponent. Okay. Here's our law. Let's take a look at some examples of why that's true. Okay. If I look at 2 to the 3 multiplied by 2 squared, and I wanted to write that as a single power of 2, what would that be? Here I have the same base, 2 to the 3 multiplied by 2 to the 2. So when I have the same base and I was just wondering if you could zoom in a little. Yeah, sure. So if I have 2 to the 3 multiplied by 2 to the 2, 2 to the 3 multiplied by 2 to the 2, then that's going to be equal to 2 to the 3 plus 2. That's equal to 2 to the 5. Let's test it out a couple ways. What is 2 to the 5? If I multiply 2 by itself 5 times. You could check your chart. You just built a little chart. It's 32. Well, let's take a look at the other side of the equation. That should be equal to 32. Okay? What's 2 to the 3? 2 times 2 times 2. 8. What's 2 to the 2? 4. What's 8 times 4? 8 times 4 happens to be equal to 32. Okay? Written another way, this is 2 times 2 times 2, that's 8, times 2 times 2, that's 4. That's 2 to the 3 multiplied by 2 to the 2. Notice I can count the number of times I'm multiplying by that. Does that make sense? You see how it's like I'm multiplying by 2 5 times if I multiply by 2 to the 3 and then multiply 2 to the 2? See how you're adding the exponents there, eh? So here's how you can use multiplication to teach yourself. If you had something like x to the 4 multiplied by x to the 2, you could write it out as x to the 4 like this. X times x times x times x. That's x to the 4. Multiplied by x squared. That's x times x. Would be equal to x to the how many? 1, 2, 3, 4, 5, 6. I just add them up. X to the 6. So I can see that that's x to the 4 plus 2. I add the exponents. You're probably not going to remember that for the rest of your life. But if you know how to reteach yourself, you'll only need to reteach yourself 2 or 3 times before you will remember that for the rest of your life. So go ahead, you have my permission to forget, but you don't have my permission to be helpless when you do forget. Use multiplication to reteach yourself. Okay? Cool. Let's keep going. How about if I'm dividing powers of the same base? Well, in this case, the rule we're going to discover is we subtract the exponents. So let's take a look at an example. Like if I algebraically write that as a rule, I might say if I have x raised to the power a, and I'm going to divide that by x raised to the power b, that will be equal to x to the a minus b. I will subtract the exponents from each other, and that will be the new exponent. Let's take a look at another example. We're going to, again, use our chart that we made of powers 3, powers 5, and powers 2 to do that. Okay, so here we go. If I have 3 to the 5 divided by 3 to the 3, what's that going to equal? What is that? You're correct. 3 to the 2 is, check your chart. No. But you would not be surprised to know that's not the first time I've heard that untruth. that 3 to the 2 is not 6. Okay, 3 to the 2 is not 6, happens to be 9, because 3 times 3 is 9. 3 to the 2 is 3 times 3. It's 9. So this is equal to 3 to the 2. 3 to the 5 minus 3, which is equal to 3 to the 2. 3 to the 5 divided by 3 to the 3. Let's do it on our calculator. 3 raised to the power 5 equals 243. Whoa, that's a big number. Divided by, not that really that big. Divided by 3 raised to the power 3, on the other hand, equals 9. There we go. The answer 9. So there's your answer. Why is that true? Let's take a look. If I write that out with multiplication, it's going to look like this. 3 times 3 times 3 times 3 times 3 is 3 to the 5, divided by 3 times 3 times 3. Well, what's 3 divided by 3? It's 1. And that's why 3 to the 0 is 1. Because it's like 3 to the 1 divided by 3 to the 1. You subtract the exponents. 1 minus 1 is 0. It's another way to know that. So 3 divided by 3 is 1. I'm 42 times 1 years old, so I don't tend to show that. Like I'm 42 times 3 divided by 3. This is 42, you know? So I don't tend to show that. So I can cancel, and cancel. And it only leaves me those other two multiplications of 3, and they happen to be on the top. So that's what I'm left with. Okay? And so if I show that with multiplication, let's say I do x to the 3 divided by x to the 2. Well, that's just going to be x times x on top divided by x times x on the bottom. And then this cancels this, and this cancels this. So I'm left with 1. So that's how I can remember that x to the 3 divided by x to the 2 is x to the 3 minus 2 is just x to the 1. It's just x. It's just x multiplied by itself once. Pretty clear? Pretty neat? Pretty easy to forget, and now easy to remember once you forget? See how I just like a mathematician prove the rule to myself when I forget? And I've forgotten these rules I don't know how many times. But then I just remind myself in the margin of the test so I don't lose any marks. Okay. Next is power of a power. These are situations that might look like this, where I have x to the 3 raised to the power 2. So if I'm raising a power, this is a power here. Remember, a power is a base raised to an exponent. So if I raise that power to another power, then I need a rule for that. Anyone remember this one? No one remembers this one. All of you forgot. But you saw this in grade 9, you used it again in grade 10, and you forget again. Just be aware that these are easy to forget, and you want to be able to reteach yourself using multiplication. When raising a power to a power, let's come back to that and we'll figure it out. Let's take a look at an example where I have 2 squared raised to the power 3. And let's write it out as being equal to 2 squared multiplied by itself 3 times. 2 squared multiplied by 2 squared. Can anyone see what that would be as a single power of 2? You see how that's 2 squared raised to the power 3? It's 2 squared multiplied by itself 3 times. Okay, so that's why it's 2 squared raised to the power 3. I just wrote it out with multiplication. Now, I could use my product of powers rule where I'm multiplying different powers and add the exponents. And what will I get? Yeah, that's right, Gabby. 2 to the 6. If I wrote this out again with more multiplication, that would be 2 times 2 is 2 squared, times 2 times 2 is 2 squared, times 2 times 2 is 2 squared. So that's 2 times 2 times 2 times 2 times 2 times 2, which happens to be 64. 2 to the 6 equals, the rule here, what did I do to this 2 and this 3 to get to the number 2 to the 6? Yeah. You multiply the exponents when raising a power to a power. Okay? And you can use these types of examples to reteach yourself. Let's say I have x to the 3 raised to the power 2. Okay? You could write that out as x times x times x, that's x to the 3, and then multiplied by itself. So that's x to the 1, 2, 3, 4, 5, 6. That's equal to x to the 2 multiplied by 3. That little dot in between means multiplication. So here, an algebraic way of writing that down would be x to the a raised to the power b is equal to x to the a multiplied by b, x to the ab. So when raising a power to a power, we multiply exponents. We multiply the exponents. Cool. Making sense? Yeah. And do you see how you, like, exponentiation is just repeated multiplication. Multiply by that thing that many numbers of times. The reason we need that type of math is if I want to know how many pages thick the paper will be after I fold it 13 times, I can't experimentally fold it and then count. That would be very difficult. And multiplying by 2 13 times is cumbersome on the calculator. 2 raised to the power 13. But it's the same math as my money grows by 10% every year in the stock market, and I want to know how much money I'm going to have after 10 years. I need to multiply by 110% 13 times. So I'm going to use exponents to do that type of math. Okay. All right. Another rule is the zero exponent rule. Anything raised to the 0 power, so I have like x to the 0 equals, what does anything to the 0 equal? Always 1. Yes, anything to the 0 power equals 1. Circle it. Put an arrow next to it. It's actually a really important fact. X to the 0 does not equal 0. X to the 0 equals 1 for all values x except 0. 0 to the 0 does not equal 1. But it's the only value of x that doesn't. 0 to the 0 is probably 0. Probably, I said. And I also don't care too much as a math teacher because we're never using that as our base for an exponent in this course. So don't worry about it. Anything to the 0 equals 1 and you are fine. Okay, let's keep going. All right, why? Why is this true? If I have x to the 0 that equals 1, okay, that's like my algebraic representation of this. Let's take a look at an example that might show us why this is. Okay, if I have x squared divided by x squared, what is that? What's x squared divided by x squared? It's 1, because I'm dividing something by itself. So if let's try some values of x. Let x equal 2. 2 squared is 4. 4 divided by 4 is 1. 4 quarters is $1, right? And then if x is 3, 3 squared is 9. 9 divided by 9 is also 1. But we get this from our exponent laws as well. This is x to the, this is dividing powers with the same base, so I subtract the exponents. 2 minus 2 equals x to the 0. 2 minus 2 happens to be 0, so this is x to the 0, and that is 1. So this is a little trick that you can use using another exponent law to remind yourself of x to the 0. Oh, wait, I forget what this to the 0 is. I'm going to use my other exponent laws that I've recently retaught myself using multiplication to remind myself about what things to the 0 equal. Well, they equal 1. Okay. And then we saw some examples of negative exponents before. Let's take a look at negative exponents. Like if I have x to the negative a, where a is some number and I'm raising x to a negative exponent. When an exponential term has a negative exponent, let's try and figure out the rule here. Let's create a negative exponent with something like 2 to the 2 divided by 2 to the 3. Cade, what's 2 to the 2? 2 to the 2? 2 squared? 4. What's 2 to the 3? No. 3 to the 2 is 9. 2 to the 3 is 8. Good. So that's a little factoid that you can remember. 4 over 8 is what? If I reduce this fraction, Bennett, what do I get? 4 over 8. Like I've cut pizzas and, yeah, it's 1/2. Good. So that's 1 over 2. Okay. But if I used my quotient of a power law and did like the exponents that way, it would be 2 to the 2 minus 3. Okay. I subtract this one from that one. All right. So let's see, what do I get there? Well, that would be 2 to the negative 1, right? If I have 2 squared divided by 2 cubed, that's equal to 2 to the negative 1 equals 1 over 2. Well, 1 over 2, I could write that as 1 over 2 to the 1. So one thing I'm noticing with this negative exponent, it's flipping things to the bottom of the fraction. It takes your base and turns it over. And that's all it does. This is a negative exponent, turns your base over, and then you keep going. So if I have something like x to the negative a, I want to remember that that's just 1 over x to the a. And I can use examples like these to prove that to me. If I had x to the 3 over x to the 6, that's going to be equal to 1 over x to the 3, but I could also write that as x to the negative 3. Stuff like this. Just flips your base. Did I lose you, B? Or does it make sense? Make sense? Cool. Good. All right. So let's simplify the following types of expressions, and we'll take a look at what they equal. All right. So if I have something like this, and I want to know what does this equal, well, I can apply my exponent laws to it to simplify it. X to the 8 over, and this is just like an elephant that I need to eat in 1, 2, 3 bites. You know, you can't eat an elephant in one bite. You have to eat it bite by bite. Well, maybe I have a very large mouth. Maybe my mouth has grown by the factor 2 to the power 5. It's 32 times its normal size. So what's the first bite here? X to the 8 over x to the 2. If I want to write that as a single power x, what is it? Well, I write it as x to the 8 minus 2. And then x to the 3 to the 2. That would be plus x to the 3 times 2. And then minus 2 times x squared times x to the 3. Well, this would still be minus 2. And then this would be x to the 2 plus 3. And so then we work it out. X to the 8 minus 2 is x to the 6. X to the 3 times 2, well, that's going to be plus x to the 6. And then it's going to be minus 2 times x to the 5. Just figure out your new exponents. And then x to the 6 plus x to the 6, what's that? If I have 2x to the 6's and I add them together. X to the 6 plus x to the 6. Danny, Sarah? It is not that. What's x squared plus x squared? 2x squared, right? I agree. Yeah. So if I have x to the 6 plus x to the 6, what's that? 2x to the 6, yeah. 2x to the 6. I had one of them and I added another one. So I have 2x to the 6 minus 2x to the 5. Can I subtract those from each other meaningfully? No. This is where I would leave the question. That's done final answer. It can't be simplified any further. Okay. I could common factor it, but I can't add or subtract those together. I could write this as 2x to the 5 multiplied by x minus 1, but I don't care. This is done final answer. That's common factored. Okay, this one here, if I want to know what this one is equal to, let's do our work. Anyone know 36 to the 4? 36 multiplied by itself 4 times? I don't. I know it's very, very big, but I'm not going to figure it out because I don't need to. Okay? So 36 to the 4. What is that? Well, I don't know, but I'm going to divide it by 36 to the 3. So what do I have here in the beginning? This is 36 to the 4 minus 3 as an exponent. Okay? Multiplied by 2 to the 3 to the 2. What's that? It is 2 to the 6. Good. So we're applying our power of a power law there. So that's 2 to the 3 times 2 divided by 16. Okay, we'll just write down 16. We could rewrite 16, though, as a power of 2. What is 16 as a power of 2? 2 to the what equals 16? Well, let's test. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. 2 to the 4 is 16. Okay, so I could write 16 as 2 to the 4. Let's do that. Instead of writing 16, let's write it as 2 to the 4. Okay. Now let's bring another line here. This is 36 to the 1. Aha, that's much easier than 36 to the 4, isn't it? All right, multiplied by 2 to the 3 times 2 is 2 to the 6 divided by 2 to the 4. 2 to the 6 divided by 2 to the 4, well, that's just 36 to the 1 is just itself, is 36. Anything to the 1 is just itself. 36 multiplied by 2 to the 6 divided by 2 to the 4 is 2 to the what? 2 to the 2, good. What is 2 to the 2? 4. So I'm just going to write here 4. 2 to the 6 is divided by 2 to the 4. And maybe I didn't know that, so I did 2 to the 6 divided by 2 to the 4 on my calculator. And I got the answer 4, and that's the answer. So 36 times 4, what's that? Oh, do that in your head, it's 144. There, done, final answer. So that one simplifies right to a number. Notice there's only numbers in here, there's no variables, so I should be able to resolve that to a single number, with or without a calculator. This one I don't believe is a calculator problem. You want to develop your mental math skills to be able to do that. 36 times 4 in your head? Well, maybe that's hard, so instead I divide 36 by 2, and I get 18, so I do 18 times 8. Maybe that's hard, so I divide both by 2, and I do 9 times 16. And then I rearrange the factors into 12 times 12, and then I have 144. Okay, sorry, let's keep going. If I have something like this that mixes both numbers and exponents, then what I do is I change the color of my pen so you know I'm working on a different question. This one is equal to 25 divided by 5. What's that? 5, okay. X to the 5 divided by x to the 5. I can use this law, subtract the exponents, and y to the 6 divided by y to the 8, I can also subtract the exponents. Okay? So 25 divided by 5, you've identified that that is 5, no problem, that's good. X to the 5 minus 5 is x to the 0. What's x to the 0? 1. If I multiply by 1, do I usually write that down? Not really. So I don't write anything. Those all cancel away. X to the 5 divided by x to the 5 is just 1. It comes out of the problem. It cancels itself. And then I have y to the 6 minus 8, so y to the minus 2. This is done final answer, but I can also write it another way. I can write it like this, 5 over y squared. And I prefer this. This earns the math smiley face for being in a better form. Because negative exponents tend to be confusing. And here's the rule with negative exponents. When you have a negative exponent like this, it takes your base and kicks it to the bottom of the fraction. Just moves that part to the bottom of the fraction. It doesn't move the 5 because the 5 was not raised to the power negative 2. Only y was raised to the power negative 2, so y moves to the bottom, but not 5. So That was a longer lesson today than we are used to, but it's the foundation for our unit. And learning these exponent laws, not only learning them, but forgetting them and then reteaching yourself with multiplication is going to be the foundation of what we do over the unit. The practice questions for you have been harvested from the textbook. They are all here. We probably want a little bit more time on this, right? Like we need more than 15 minutes or 10 minutes of practice. So we'll practice this more tomorrow and have a shorter lesson, if a lesson at all. Any questions, hit me up by email, Team Learn at Home. Otherwise, thank you for showing up for your learning. Okay, I'll come around.